Hey, what's up you guys? Welcome back to another video. We are talking about function transformations in this video. So we are now in section 1.3 in Stewart. And our objective here is to identify and apply common transformations to functions and their graphs. What we want to remember is that when we start with a function is a mathematical object that we can do things to, just like we do with numbers. And what we'll be doing here is we're going to be obtaining some new function g that's related to f some way by way of some transformation capital T. The actual notation for function transformation is going to be whooshed away into the details. But importantly, given any function, we can apply three fundamental kinds of transformations that we'll discuss in these following videos. So the first is what we call translation. And in less formal language, we mean shifting, either vertically or horizontally. The second type is dilation compression. And this is the kind of transformation where we're actually rescaling, again, either vertically or horizontally, and the rescaling can be squishing or stretching. The third here is reflection, about the y-axis, about the x-axis. There's all sorts of forms, but this kind is easier than the other ones, interestingly enough. So before we begin, remember that transformations are functions themselves, but of functions. So we're talking about functions of functions, and that's the most that we'll ever get to in terms of the depth of the mathematical constructs involved here. But they can be combined and undone. So you can apply a sequence of different transformations in a specific order, and then you can undo them as well. And the order often matters. Okay, so one thing to keep in mind is order does matter. Not always, but in general, we should be careful. All right, so here we'll talk about first translation. So shifting. Okay, the first kind that we discuss here is vertical shifting. This one's easier to talk about because what we're going to do is we're going to manipulate the y values. So the two kinds that we can do here are g of x equals f of x plus some c, where c is a real number, or f of x minus c, where again c is some number. And so what we're actually accomplishing with these two transformations is we are either shifting up by c units. We're going to assume that c is a positive real number, and we're shifting down c units. Okay, so to understand what we're talking about here, our prototype, right? Let's get a coordinate grid going here. And I'm going to draw this function. It's going to be f. And on the same graph, we're going to plot a g and an h, which would be either a shift up or a shift down. Okay, so this is my f function. What you want to understand this is this is a piecewise function made up of two linear functions. Okay, and it passes through three important points, right? It passes through 0, 0, through 1, comma 2, and through negative 2, comma 1. All right. Now I'm going to use two different colors for the shift up and shift down. So shifting up C units, okay? So this function that I'm about to graph is going to be g of x equals f of x plus 1. So we're shifting up 1 unit, okay? And what you can do is you can imagine taking these points and just adding 1 to each of the y values that we obtain. So in this case, what you can see here is that we actually get two sets of parallel lines corresponding to both parts of the piecewise function, okay? And so for each function value, you're just adding 1 to the y value, okay? On the other hand, if we're shifting down, we're going to take away some number of away from the y value. So let's do f of x minus 2. So that means all our points are going to get shifted down 2 units. So this is our, whoops, there we go. This is our h function, okay? And I forgot earlier to label this g, but we were talking about it. Okay, so again, notice the only thing that's changing is not the x values of the points, but just the y values. We're subtracting 2 from each one. All right, so the key insight here, just add or subtract from the y values. That's not too bad. All right, as for horizontal shifting, horizontal translation, now we're going to have to manipulate the x values. And when you're manipulating the x values, you're going to have to represent the function differently than what you might expect. In fact, the exact opposite. So there are two types here that we're going to discuss. We're going to obtain some new g function from f by applying f applied to x plus c, and h of x equals f of x minus c. So to understand this, right, these are the new x values, same y values. And you're changing them so that, I'm going to use the color scheme again. So the first one, f of x plus c, is actually shifting left c units, while f of x minus c shifts right. And you'll see how that works in a second. We're going to do another illustrative example here. So let me place my coordinate grid. All right. And so here, what we want to think about is this is going to be something along the lines of, so our f of x looks kind of like x cubed. And we're going to form two new functions. So g of x is f of x plus 1. So that should result in a shift left by 1 unit. And h of x should result in a shift right of 3 units. Okay, so let me set my axes again. right, so the original function, right, is x cubed. So remember that passes through the origin, passes through these points, and looks roughly like this. Something like that, okay? So passes through 0, 0, through 1, 1, and through -1, -1. Makes sense, right? It's odd. Now, if we're shifting left by 1 unit, I'm going to take all the points that I had here to set up the curve. I'm going to show you that this is actually what we want. So 0, 1, -1, 0, and -2, -1. Okay, so how do these points relate, right? So remember, we said what we're going to do is we're just going to assign different x values for the same y values. So what you want to associate is 0, 1 was obtained from 1, 1. Okay? So g of x says for every x in the domain of f, add 1. Why does this work this way? Because in order to obtain the correct y value, you have to add 1. So it's giving you a blueprint for figuring out how to obtain the new points. You just have to do the opposite of what inside the parentheses tells you. I know, it's weird, but it works. So similarly, if we're going to shift right 3 units, that means each new point is actually obtained by adding 3 to the x value, while keeping the y values the same. And there's the curve. Not the greatest imitation of a cubic curve, but there it is nonetheless. All right, so the key insight here is that we're going to change the y values, no, the x values, I'm sorry. So change the x values in a way opposite of what you expect. So in other words, for example, f of x plus 1 actually means subtract 1 from each x value. Okay, now let's see an example real quick. We're going to pull together what we just found. Okay, so our example here, we're going to take our function to be 1 over x. And so we're going to find 2 transformations. And then we're going to write the function statement and sketch the graph. We'll do this separately so that we have the parent function and the child. Okay, so importantly, when we say we have some original function f, this is what we call the parent function. And when we say for each, we're going to get some new g or h. These are the child functions. There's actually nothing relating them in terms of one's more important than the other one. We're just saying that we're obtaining these new functions from this original one. Okay, so number 1, we're going to shift down 2 units. All right, and so that means our g of x is going to be, remember, what do we do here? That's f of x minus 2. So we want to express that in terms of the original function. That's 1 over x minus 2. And you can leave it like that. You don't have to do anything else. So that's our new function. And now let's graph them. So we'll take some sample points, right? So the original function, it goes through, so let's go 1, 2, 2, -1, -2. All right, the original function passes through 1, 1, through -1, 1, through 1/2, 2, and through 2, 1/2. And then similarly on this side, -2 gets assigned to -1/2. And then if you plug in -1/2, you get -2. Okay, so this is our original curve, is f. Again, f. And maybe we'll need to actually extend this downward. Oops, that's not great. And so for each of these points, right, we're actually shifting by down. We're shifting down by 1. So I'm going to use this color here. All right, so shifting down by 2, sorry. So this point, this point, this point. So it should look more like that. And similarly on this side, right? So pull that down 2 points, 2 units, pull that down 2 units, pull that down, oh sorry. If I'm pulling that down 2 units, it should be more like this. And there's your curve. This is G. All right, so it doesn't look exactly like what we expected it to, right? But if we extended each of these functions downward, right, so that they actually match the trend here, then you can see how they are just a translation of by down, down 2 units, right? So the midpoint here now is -2, 0 rather than the origin. That's the reflection point for this, if this was an odd function. Okay, now transformation 2, let's shift right 1/2 unit. Okay, so again, what are we doing here? G of x equals f of x minus 1/2, because we want to do the opposite of the actual transformation inside the parentheses, which means that wherever we have x in the function statement of f, we're going to replace that with x minus 1/2. So that's going to be 1 over x minus 1/2. And you can write that if you're not comfortable with the complex fractions here, you can actually multiply both the numerator and the denominator by 2, which should give you 2 over 2x minus 1. Okay, so let's graph them. Again, I'm going to have to graph, 1 over x first. So, you can fast forward through this if you want, because this is just a repeat of what I did earlier. But our point here is that, here we go, this is f, and then this, I should have called it something else. I should have called it h of x. So h now, remember, we're shifting right 1/2 unit. So each of our points here is going to be moved to the right 1/2 unit. So 1/2, 1/2, 1/2. That looks roughly like this. And then similarly here, 1/2, 1/2, and I guess that should have been right here. So it should look like I'm not super precise right now because my scaling is not perfect, but there it is. So we've shifted now by 1/2 unit to the right. So in the next video, we'll talk about the other kinds of function transformations and see how we can do all of them at once.